Section 3.6 is called curve sketching. And basically, what we're going to be doing in this section is taking everything that we've learned so far in this course, and really actually everything that we've ever done with graphing ever since like 8th grade, and putting it together in this one section to be able to graph complicated functions in sort of a clever, I guess, way, without just reaching for the calculator and graphing it absent-mindedly. We're going to be able to understand what the function is doing using calculus and using all of the techniques and parts of the graph algebraically. Okay, so it combines everything that we've done so far in this section. So, and everything we've done so far this year. So, like x and y intercepts, symmetry, domain and range, continuity, vertical asymptotes, horizontal asymptotes, slant asymptotes, differentiability, the relative extrema that we've been talking about, concavity and inflection points, and then limits at infinity. So all of the things, all of the aspects of these functions that we've been talking about are going to come into play here as we try to sketch each of these functions. So we're going to use all of this knowledge and combine it all together to create a reasonably accurate representation of functions without sitting there and doing like we would do in Algebra 1, which is just making a table of values and plotting points. Okay, so we're trying to use our skills to do something a little bit more advanced. So here you go. Why do we care? So we currently have three methods of graphing at our disposal. So I want to try to list some pros and cons of each of these. Okay, so plotting points, which is what we would do back in Algebra 1 all the time. And then in Algebra 2, anytime we encountered something that was new. We have using calculators, so technology type stuff, right? We can always enter a function into a calculator and graph it and see what it's looking like very quickly. And then calculus. So that's the sophisticated methods that we've been developing for a while now. We just haven't really put them together, as like we're about to do in this section. So pros and cons. So something like, say for, okay, let's write. And let's pick a color. Okay. So something like 4x to the fourth plus 6x squared minus 5x plus 1. So back in Algebra 2, you learned some techniques to be able to at least visualize what this graph could possibly look like. But back in Algebra 1, you would have no idea how to do that, and so you would have to plot points, and it would take you forever. Okay? So plotting points, primitive method, you would have to make a table. Okay? So what are some pros? Well, you can plug in points and go with it, right? Plug and go. You can draw curves. As long as you get enough points, right? So there's a little bit of a caveat with that one. You can draw curves as long as you have enough points. If you don't have enough points, it could wind up looking like a line. If you don't know anything about what a polynomial looks like, you might not get all of the curves. You might just get end behavior in one spot, okay? So what are some cons of plotting points? Well, one is it takes forever. That's the big one. You got to pick enough points. For it to be meaningful. You could have the situation where, we have a dot here, and a dot here, and it looks linear, but for sure it's not. Okay? So there are definitely some disadvantages to the plotting points approach. Okay, so let's go on to using a calculator. What are some advantages to using the calculator? Well, it's quick. we can quickly see what the graph is doing. Okay, so we can see it right away. What about we can zoom in and out, right? Zoom in and out. So it's nice for finding analytical type things. Nice for analyzing stuff. Like if I want to find an intersection point, that's nice. If I want to find a zero, that's nice. If I want to find, you know, for our purposes, as we approach a limit where the function is discontinuous, we have a hole or something like that. That's nice. Stuff like that. Okay. So what are some disadvantages? Well, the big one is image quality. Image quality, IQ. Okay. Um, Image quality can be bad. So, for example, we had earlier this year, I gave you an example of an infinitely oscillating function. As I get closer and closer to some value, the function is oscillating more and more and more and more and more, right? As we get closer and closer to that infinite oscillation from each side. Image quality starts to fall apart as we get closer and closer to that. We're kind of limited to functions. That's not exactly true. Depending on your calculator, depending on what's capable of doing, depending on your knowledge of the calculator. But for the most part, most people kind of limited to functions. You have to zoom. Can be a distraction. Zooming is an advantage, but it's also a disadvantage because of the window that you're depending on. You have to know how to zoom. You have to understand the function well enough to be able to know when you need to zoom and when you don't. Also, limits on technology. If you're relying on your calculator all the time, you're never going to learn when there's a hole because the calculator is never going to show you that hole. Okay? It just doesn't. No matter how much you zoom in, you're never going to see that hole. So, what I'm getting at there is over reliance. You rely too much on your calculator and you never really learn how to multiply numbers together. You never really learn how to add. And it's one of the saddest things when you look at your calculator and the last person to use it had to type in like 4 plus 6. They never really learned it because they relied on their calculator too much. Okay? The calculator can be misleading. You go to graph something and you see this on your screen. Okay? Is it a line? Maybe, maybe not. I don't know. But it looks like one on my window. Okay? So it's misleading sometimes. And this one's going to sound bad, but dumb users. Okay? The calculator is only as smart as the person who's using it. If the person who's using it doesn't really know how to use it, then it's not going to go so well. Okay? So using a calculator can be great, but it can also be terrible. It just depends on a lot of things. So it's a powerful tool, but it can also be really dangerous. So calculus, some pros and cons. So if I'm using calculus, then when I'm dealing with calculus, I know when I have a horizontal asymptote. I know when I have a vertical asymptote. I know when I have a slant asymptote. Okay? I know when I have a hole. I know what the graph is going to do as I approach a horizontal or a vertical asymptote. I know what's going to happen with an infinitely oscillating deal. Okay? I know these things because I've learned the math behind it. And I can use that math to tell me. The math starts to talk to me rather than having to rely on plotting points or having to rely on using a calculator. I start to learn what the math is telling me, what the equations are telling me. I start to speak the language instead of having to rely on other things to tell me. Okay. So basically, what I'm saying here is we can use features that are present in functions to reduce points needed to graph. Okay, so we're still plotting points. We're still kind of plotting points, but it's not really plotting points anymore. We're using the features that are present that we know about, like asymptotes and function behavior, concavity, and increasing, decreasing, and stuff like that, to be able to minimize the amount of extra work that we need to do. And we can come up with really accurate graphs very easily without having to take forever picking all these points and stuff. Okay, so that's the idea, right? Okay, so let's see what's next. So I'm going to give you some steps on how to graph functions using calculus, and that's as far as I want to get in this section today. And then, so this video is just basically an introduction into what we're doing. Here are the steps for graphing functions using calculus. And then further videos in this section are going to be the practice problems. So this is just the introduction. So steps for graphing functions using calculus. What you're going to do is you're going to take the first derivative and the second derivative, because you're going to need to find your critical numbers and your inflection. Okay, you're going to need to find where you're increasing and decreasing and what your concavity is. Okay, so you need those first and second derivatives for sure. So you might as well take them right away. All right. Now, actually, one of the first things I'm going to do is I'm going to look for X and Y intercepts. I'm going to look for discontinuities, vertical asymptotes, and stuff like that. Okay, so I might do step 2 and step 3 here, and step 4. I might do those first before I take the first and second derivatives. Just get those easy ones out of the way. Okay, so I have step 2 here. I say find the y-intercept and all the x-intercepts of the graph. And you do that by setting x and y equal to 0 and plot those points. Okay, plot the points. So you start graphing right away. Plotting points, easy to do. Okay, now step 3, I might, like I said, I might do that right away before I take the first and second derivative. Do we have any discontinuities? Are there any holes? Are there any vertical asymptotes? Are there any slant asymptotes? Okay, are there any horizontal asymptotes? So basically I'm doing 3 and 4 kind of at the same time. If I have any of those, if I have vertical asymptotes, I'm going to find them and plot them right away. They're going to be dotted lines. Okay, if I have any holes, I'm going to make note of those. Okay, a hole at x equals 5 or whatever, I'm going to note that, and I'm going to make sure that I mark that hole when I go through it as I make my graph. Okay, if I have horizontal asymptotes, again, find and plot them as dotted lines. Slant asymptote, we need to remember how that slant asymptote occurs. When does it occur? So pay attention to the degree of your rational function on top and bottom. Do you have a horizontal? Do you have a slant? If you do, find it and plot it. Okay. Now, at this point, usually, so these guys right here come in a big chunk. When I do all of those, usually I do those first, and then I do the first and second derivative. Okay. Then, once I have the first derivative and second derivative, I go ahead and find my critical numbers by setting the first derivative equal to 0, set the second derivative equal to 0. Okay. I find those critical numbers and I find my inflection points. Now, with these two right here, these two guys, you find your critical numbers and your inflection points. You want ordered pairs. Okay? You want those ordered pairs for critical numbers and for inflection points. You want both, because you're going to plot points. You're going to be making a graph. So you want to get ordered pairs for both your critical numbers and for your inflection points. Remember that vertical asymptotes are also critical numbers and inflection points. You don't need ordered pairs for those because they're just vertical asymptotes, but they are part of your inventory for critical numbers and inflection points. Okay. So now I missed something here. There should be another line set up. So like right in here, squeeze something in right there. So right here, I'm going to set up intervals and choose test numbers. Okay, now the intervals, test numbers, the intervals will include critical numbers, inflection points, vertical asymptotes. Okay, so all of your critical numbers, all of your x values for your inflection points, and all of your vertical asymptotes will all go in your intervals. Your x-intercepts will not. You do not include those. Okay, now you're going to check your concavity and test for increasing or decreasing. So you're setting up your intervals there, okay? So you're going to have intervals, bunch of intervals, maybe a whole lot, okay? Your table now is going to look like a combination of critical numbers and inflection points. So you're going to have x, your test values. You're going to be plugging x into f if you want ordered pairs. Now you don't have to do that. So actually, I'm going to skip that. F prime, you want the first derivative for increasing, decreasing, and you want f double prime for second derivative, concavity. Okay? So ignore this down here. Sorry about that. I'm tired. There we go. See, it's beautiful. Okay. So test number, f prime for increasing, decreasing, f double prime for concavity. Okay? So we got all of our intervals set up and we're ready to go. All right? Then what we're going to do is create a smooth sketch using all of our known information. Okay? Now, in each one of these intervals, we're going to decide that we're increasing in concave up, or increasing in concave down, or decreasing in concave up, or decreasing in concave down. There's only 4 ways that this can go. Okay? But you got to also remember that you can have a vertical asymptote. Okay? Now let's say there's a vertical asymptote right here. What I would do is I would mark that VA right there. Okay? And maybe there's another vertical asymptote right here. So like we're going from negative infinity to, I don't know, -2, and then from -2 to -1, and then from -1 to something, right? So at -1 we had a vertical asymptote, so I'm going to mark that so that I know that there's a vertical asymptote right there. And then I have another vertical asymptote right here. Okay, that's it. I'm going to mark that on my table so that I don't screw up and accidentally think that I need to incorporate some sort of thing between those two intervals, okay? The reason I'm saying that is because of this. There's only 4 ways that we can have our graphs go, okay? When we're done, let's say in this table here, we were decreasing and concave up. And then we were decreasing and concave down. And then we were increasing and concave up. And then we were increasing and concave down. Okay? Just as an example, because I want to show you what these each look like. Okay? So decreasing and concave up. Decreasing first, but concave up looks like this. Okay? Now decreasing and concave down, that looks like this. All right? Now increasing and concave up, that looks like this. And then increasing but concave down, that looks like this. All right? So, like I said, there's only 4 ways that these graphs can go. And as you work your way through the table, once you have a combination of increasing or decreasing, concave up or concave down, then you need to piece together what the shape of the graph is. And that's going to help you come up with what the overall graph looks like, okay? And you'll see as we get going in these examples, you'll see once we start piecing together what the graph looks like, how the graph must look when you finally make your final overall sketch, okay? So this was just the introduction, like I said, and the next video is going to give you, just start giving you examples, and it's very important that you both pay attention to the examples and get after the homework right away so that this starts to sink in, because curve sketching is kind of a big deal for us. All right.